myself Vikash Gupta, and today we are back with experiment number 3 of the digital signal processing laboratory, which deals with the application of autocorrelation function for analysis of signal. So, aim of the today's experiment is to compute the pulse rate from a given PPG signal data and the pitch period of a speech signal using the autocorrelation function generated in Arduino IDE platform. So let's get to know what is autocorrelation. Autocorrelation, also called as serial correlation in digital signal processing, refers to the correlation of the signal with the delayed version of itself as the function of the delay. Basically, it gives the measure of the similarity of the signal samples as a function of time lag between them. The equation for the autocorrelation function is as follows. Now, let's talk about some of the properties of this autocorrelation, basically autocorrelation function. At zero delay, it gives the maximum value which is equal to the energy of the signal. As it is self-understood that at zero delay, the signal will coincide with itself giving the square value, that is the energy. Also, it is an even signal. It is a periodic signal for the periodic signal with the same period and aperiodic for the aperiodic signal. And finally, it is a monotonically decreasing in nature. Let's talk about some of the applications of autocorrelation. It is used to estimate the dominant fundamental period of the signal. It is also used to determine the periodicity of the signal buried within the noise. It is used for the pattern recognition and detection purpose in signal processing. And finally, it is used for removing AWG, which stands for additive white Gaussian noise, the most basic form of the noise. Now, let's come to the lab assignment. So the first part of our lab assignment is today is to compute the pulse rate from the given PPG signal using the autocorrelation function in real-time Arduino prototype platform. The assumption which we had regarding the given PPG data is that it is being sampled at 100 Hz at the resolution of 10 bit, and we are considering a frame duration of 5 seconds to determine the pulse rate from PPG signal. So first, uh, before just we are considered an array of data which has 2000 samples. Now, firstly, we are taking only 500 samples of data, that is basically stands for 5 seconds. So before carrying out the autocorrelation, we also need to standardize the signal to process it after that. So before that, first we will smoothen the signal using the moving average filter, which is already discussed in the previous experiments. Now, we'll take out the mean average. As we can see, basically we are finding the sum of the given PPG data, dividing it by the number of data samples to get the mean. And finally, we are subtracting the mean from the original data to get set back the reference back to zero for both the original data signal and the smoother signal. Here X stands for the original data signal of 500 samples and SM is the smoothened version of the same. Now we need to normalize the data to restrict it between -1 and 1 for standardization. So for that purpose, we have written this set of code, which is basically finding the maximum value in each of the SM and X array and finally dividing the every value of the SM and X respectively with their maximum to bring them between 1 and -1. And finally, we are using the standardized value data values to find the autocorrelation function. Here, the AC function which I made is based on the same formula which we have discussed below in the slides. Now, let's talk about the further methodology we need to calculate the period of the given PPG signal. So firstly, we need to calculate the first zero crossing point. As we talked about that autocorrelation measures the similarity of a signal. So basically zero crossing in the autocorrelation function states that there is no similarity in that function, which is implying similarity is zero. Now after that finding the first zero crossing, our aim is to find the first location of the maxima starting from that zero crossing point. So what basically we have done is to make an array starting from the first zero crossing point which we have found from the previous function. Now we are calculating the largest value in the array which starts from the first zero crossing point up to the nth value, which is the length of the data in each of the both autocorrelation function arrays which we had for the original PPG data and the smoothened PPG data. Now, Now, finally, to get the pulse rate, what we will do is to use this formula, which is basically 60 into Fs divided by maxi log. So let's understand this formula. Firstly, we will divide the location of the first maxima with the sampling rate, which is 100 in this case, in order to get the value in seconds. And finally, we are dividing the pulse period by 60 to get the pulse rate in bits per minute. And finally, we have done the same for the smoothened data. And in order to get the error between the pulse rate for the smoothened version and the raw PPG data, we use this error formula. And this set of code we have written to monitor the observation on serial monitor, which we will observe in the next stage. As we can see here, there are basically two sets of data, that is PPG pulse rate for the smoothened version and the raw PPG data, and there is error. As we can see that the error for all the four blocks of data of each of 500 samples is within 5%, and even for one set of block, the error is zero, which implies that our processing method is quite accurate in nature. And this curve basically represents the this blue curve represents the blue PPG data, which we have already been recorded using Arduino sensor. This red one represents the smoothened version of it. And finally, this green one represents the autocorrelation function. As it can be seen evidently that this autocorrelation function follows all the properties, starting from having the maximum value at z equal to 0 with periodicity as same as the signal of which it is autocorrelation of, as you can see this thing, and it is also decreasing in nature. Moving on to the next question. The next question is to compute the speech period of a speech signal which is using the same autocorrelation function in real-time Arduino platform. So here also what we did before is that we recorded the signal using mic and then tabulated in form in Excel sheet, followed by converting it to CSV file, and then here we got the data. Again, we will follow the almost the same procedure with slight changes. The last time we took sampling frequency as 100 Hz at which it is being recorded, but since the sampling rate for recording speech is generally 44.1 kilohertz, but here we are going to take the smallest value, which is 8000 Hz, to do so in order to get the lesser number of samples. And the other thing is that we are again going to take 500 samples of block each. Since we have total 4000 of samples and we are taking 500 sample blocks, so we would have 8 blocks of data. So we will estimate about 8 different speed signals. So firstly, here also we will smoothen out the signal using the previously used moving average filter with a window of 30. Moving on, now we will take the mean average of it by finding the sum for each of the raw speech data and smoothened data, which is being done in these loops. And finally, we will divide it by the total number of samples of blocks, that is 500 each. Now we will subtract the mean from each of these data, smoothened and raw data set, to set the standard back to 0. Followed by this, we will do normalization before carrying out the autocorrelation, as it is being discussed that we first need to standardize the signal. So for the normalization, we will follow the same process. That is, we will find the maximum value for the array, followed by dividing that maximum value with each of the value, which would restrict the data between 1 and minus 1. Finally, we will feed the smoothened formalized speech data and the raw smoothened speech data to the autocorrelation function, which we have made using the formula discussed in the theory part. As a result, we will give the autocorrelation area of smoothened data and autocorrelation of raw speech data. Now let's carry out the further procedure to find the period of the speech period of the speech data. Firstly, we need to find the first zero crossing point, that is the point where the similarity of the signal with itself is zero. Now we need to find the location of the first maxima starting from that zero crossing point, which we could done using that reference zero crossing point, into which is the first zero crossing point, and considering the autocorrelation function. We will find the location of the maxima. As soon as we find the location of the maxima, at that point, the similarity of the signal with the delayed version of itself is same, implying that some periodicity exists in the signal. So, if we consider the distance between the first zero crossing point and that first maxima, it would basically give the time or the distance after which the pattern is being repeated, the signal is being repeating the pattern, that is basically the period. So in order to do that, since we are doing everything in terms of sample, firstly we need to convert it into the actual term. Since the signal is being recorded at sampling rate of 8,000, so firstly we need to divide the signal by sampling rate, that is fs, that is being 8,000 hertz in this case. Since pitch frequency is nothing but just 1 upon pitch period, and pitch period we know that is location of maximum from the first point divided by sampling rate. So here just we are dividing by 1.0. Like last time finding PPG, which in terms of bits per minute we divided by 60, but here we will just finding it bits per second. So we don't need to divide it by 60. Now finally, to find the error for the smoothened and raw speech data, we will be performing this error calculation formula, followed by using the serial monitor to display the data. So as we can see here, the pitch frequency for different blocks of speech data is as follows. Here, since we have talked that would have 8 blocks of data, but for convenience, I only displayed the output of 4 data. As we can see here, the 4 data for the smooth and speech data is in between 150 to 140 to 200 hertz, which is the typical frequency for human voice for in general for male or female both. Well, and our answer is also within that. And if we talk about the error regarding the regarding the speech data and regarding the pitch period of the raw speech data and student speech data, the error for three of the blocks is 0 and one is 1.85, which is implying that our processing method to determine the pitch period and pitch frequency is quite accurate. And here you can see that this blue colored one represents the recorded speech data. Red colored one is the smoothened version, which is almost the same. And here green colored one is the autocorrelation function, which is quite satisfying all the properties of autocorrelation. That is starting the maxima with at z equal to 0 with decreasing in nature, and the periodicity of this autocorrelation is almost as same as the signal. So I conclude with this. So thank you for listening.